Okay, so welcome to our spotlight session on Intel Xenon processors and the use of the high bandwidth memory nodes. So these are the new nodes we have available on Young. We have 30 of these available, and the talk today will cover basically how these work, how best to use them, and hopefully some of the use cases, including benchmarking. So I'll pass over.
Yeah, so thank you, hi everyone, and thank you for having us here. So today we have, so I'm here from Intel. I'm Fouzhan Hosseini, solution architect, HPC solution architect at Intel, and we have also Roshira, so he's a principal engineer in Intel, focusing a lot on HPC software enabling and optimization, and lots of experience on using, on enabling people with, you know, the technology that you have today, Sapphire HBM, and also the follow-up on that one. So I start just saying that, yeah, this is today, of course, because you have CPU Max series in your cluster, we're going to be focused on that. But Intel basically with the Xeon processors, as we have seen in the last couple of years, decade, and the number, of course, have been increasing, but the memory bandwidth hasn't been increasing or with the same speed. So, and there are a lot of applications that benefit, they are more memory bandwidth bound. So with the recognition of this, Intel started to have specific solutions for this domain, for this type of application. So in 23, so we launched Intel Xeon, fourth generation Intel Xeon processors, which was codenamed Sapphire Rapid, and at the same time it was this sibling architecture, Sapphire, which had HBM on the die. So, and that,
Bhushan, just to
yeah,
interrupt, sorry.
yeah.
Your slide is not changing, at least for me. Are you changing the
Okay.
slide?
No, I haven't changed it so yet.
Okay,
It's the
sorry.
headline, right? Okay. So in follow-up, so we launched Xeon 6 in September last year. So we still have solutions for this application, for this type of needs, like for when you need more bandwidth. So that's just the high level. But as I said today, because you have Intel CPU Max series in the cluster, we are gonna be focusing on that one. And the beauty about all these solutions, the focus is that they are very easy to use. It's more or less out of the box experience. So the software don't need to really go and change anything. You don't need to go change anything in your software. So basically you run it and you benefit from improved performance. So the talk today, we're gonna give a very short introduction about the architecture, about the CPU, not going to details, but mostly focusing on different memory modes that it comes with, and how to run and use each of these modes. For people who use the nodes in the cluster, most of usually it is configured in a way that it is configured, and then you kind of use it. But it's good to be aware of this different configuration. And it's a small audience, so please stop us where you have a question. Please just speak up and ask the question. So don't wait for end of the talk. So just going back, reiterating on CPU Max series, as I said, it was designed for applications that need more memory bandwidth. That's very common in HPC, AI, analytics, so like a lot of CFD codes, for example. It is the first x86 CPU that integrates HBM onto the processor package. And the value that it brings to customers or to users is basically improve TCO, because if you're running memory bandwidth application, it generally improves your time to solution. It can improve your time to energy to solution as well, and also it can be used independently without DDR. So that has all our other sort of like TCO benefits. But again, because today is more focused on like how to use the system, I'm not going to go into the details of the other type of benefits that it has. So very high level, You can see on the top right a diagram of a Sapphire or a Fouzhan Intel CPU plus HBM. So if you look at the die, this is exactly the same thing that exists in a fourth gen architecture, and this basically you can see the HBMs on the die as well. So there is 64 gigabyte per socket, so usually you have a 2-socket node, so it's 128 gig, and then the bandwidth is like more than 1 terabyte per node, per socket, sorry, and in terms of capacity, yeah, it's more than depends. So if you have a 32 core SQ, so you got about 2 gig per core with of 4 HBM. So this is high level HBM. As I said, it is based on the same architecture as fourth gen architecture, so it does support DDR as well. So in addition to HBM, which is on the die, and the CPU can basically boot just using HBM. It doesn't need to have DDR, but for the cases that I need more capacity, it has the same level of support. So it has 8 memory channel, the same level of memory speed, 4800 mega transfer per second, that, the system can be populated with DDR. And that's what you have got in this cluster. So you have fully populated DDRs. Then that can be basically mapped to two type. It can be used in two ways. It can be configured as so the software can see HBM and DDR as the different address spaces. So it gives more control on what you run on HBM and what you run on DDR. And also it can be configured in a way that HBM is completely transparent to the user. Yeah, so it kind of works some way middle and then like a cache between DDR and actual cache. So it's easier to use, but you have less control. But Roshiro is gonna go into more details, so I keep it high level here and hand it over basically.
Okay, thanks, Fouzhan. So the way the HBM is exposed to software is through memory modes. So there are 3 memory modes that you can configure the processor. They are configured at boot time in the BIOS. So the users cannot change them. You have to reboot the machine to change the mode. So there are 3 modes as Fouzhan alluded to. So there is HBM only when you don't have any DDR installed. And then in the middle, you have DDR installed, and both DDR space and HBM space is exposed to software as 2 different memory spaces. We'll go to that in a little bit. And on the right, finally, you have cache mode, where the HBM acts as a transparent cache to DDR. So the software would not see HBM because it is transparent. It's a hardware managed cache. Software will only see DDR, so you would run your applications just as you would on a DDR machine. But you have to be aware of a few things, and we will touch upon those things a little bit later. So those are the 3 memory modes. As I understand, the current cluster is mostly configured in the cache mode, and you have plans to go to flat mode. So mostly we should be at least put some nodes in flat mode. So that's what I understood from communication that I received. So HBM only would be mostly of academic interest, but we will look at both flat and cache. Okay, let's go to the next slide. Okay, so orthogonal to the memory modes, the processor can be partitioned. The resources on the processor can be partitioned into clustering modes. So there are 2 clustering modes. One is called quad. Essentially, when you don't have any clustering. So that's on the top right. And on the bottom right, you see a picture where the resources are partitioned. That is, both cores, HBM and DDR are partitioned into 4 partitions. And this is called subnuma clustering, or SNC4 for short. And for this is for each socket is partitioned into 4. So if you have 2 sockets, you will get 8 partitions in total. And so each of these partitions have cores, DDR channels, and HBM as shown in the picture. So this is to provide higher bandwidth and lower latency, because within a partition, you have lower latency from cores to HBM and DDR. To use SNC4, you need NUMA-aware software, because each partition is exposed as a NUMA node to software. So the applications have to be NUMA-aware. So fortunately for HPC applications, the HPC applications are usually MPI applications, which are NUMA-aware. So you can easily run 4 MPI ranks on these 4 NUMA nodes, as you would on like 4 sockets. So that's the way you would use the SNC4 clustering mode. Okay, so next slide, please.
And
Okay.
I think as we were just talking with Heather offline, I think you should have SNC4 activated because you had a NUMA node based on what you said.
Yeah. So when you combine memory modes and clustering modes, you get this matrix where you have memory modes in columns and the clustering modes in rows. So you would have, for example, HBM only can be either quad or SNC4, or flat can be the quad or SNC4, and cache can be the quad or SNC4. But since I heard that you will be using this mainly with SNC4, you have to look at only the bottom row and flat and cache cases of the bottom row, the rightmost and the middle one in the bottom row. So we'll emphasize those 2 modes, 2 options, but we will look at other options just for completeness. Okay, so let's start with the HBM only mode, just for completeness. So with HBM only mode, you don't have any memory. You don't have any DDR. The only memory available is high bandwidth memory. So it's like the usage is just like using another DDR machine. You don't have to do anything. Your application will use HBM by default, and you can run your application, MPI application, as usual. But you have to take a few things to make sure that your application can fit within the HBM space, because HBM memory space is limited. Okay, I think so. So you can have that in both quad and SNC4. This is the SNC4 option. Again, you just have HBM and you have 4 nodes on each socket. So that's the difference between SNC quad and SNC4. So since you have DDR installed, this is not very interesting to you. So let's go to the next slide with flat mode, where DDR is present and DDR is exposed as a different NUMA node. So let's start with quad. So this is not the option you currently have, but if you were to have only quad, then the DDR nodes. So to begin with, software sees both DDR and HBM. Both memory spaces are exposed to software, and DDR nodes have cores attached to them, as shown on the picture. And if you look at a NUMA control output or something like that, you will see that nodes with DDR are enumerated first, followed by HBM nodes. For example, in the top right picture, you will see that node 0 has a DDR and cores attached to them. And on the socket 1, node 1 has DDR and cores attached to them. And then you have node 2 and node 3 separately for HBM. So node 0 and 1 are DDR with cores, and 2 and 3 are HBM only. So that's the summary. So in the flat mode, by default, applications use DDR. So it is very easy to use. If you don't want to take advantage of HBM, if you just run your application, the application will reside in DDR. So it appears like just another DDR machine, right? And it won't touch HBM, so you won't get any benefit from HBM, but it will run using DDR with because DDR higher capacity. If your application has higher capacity and doesn't benefit from higher bandwidth, you can just run it, and it will function as another DDR machine. If you want to place your application specifically in HBM, if it is a high bandwidth application, an application that can benefit from high bandwidth, then the easiest way to do that is to use NUMA control option. NUMA control, a utility that comes with Linux. You can, with NUMA control, you can place the entire application in memory. The command is given here, NUMA control -m. So -m says membind. You will put the entire application in HBM space. That's good if your application can fit completely within the HBM, but if your application cannot fit completely within the HBM space, then you can use this preferred menu option. That is, operating system will prefer HBM when it is allocating memory. So the pages that are allocated first will go to HBM, and then any other pages that overflow will go to DDR. So you can use HBM that way easily without modifying your application. So alternatively, that is instead of using NUMA control, you can, if you are using MPI, you can use 2 different MPI variables to place the application in HBM. Then you don't need NUMA control. If your application is already MPI, you can just use this Intel MPI environment variables and place the application in HBM. So both those options, either NUMA control or MPI, do not need any changes to your software. But if you really want to go and change your software, you can do that with program modification. There is a library to place heap structures in HBM, but most users don't have to do that, and you can mostly use NUMA control or MPI environment variables. Okay, so let's move on to the next slide. The only difference between this slide and this previous slide is now we have SNC4 in the flat mode. So now you have more cores. Still, the rules are the same. Nodes 0 to 7 are DDR with cores, and 8 to 15 are HBM. So the DDR nodes are numbered first, followed by HBM only nodes. Again, you can use NUMA control and MPI variables to place your application in HBM. The only difference is that node numbers have changed now because you have more nodes. Altogether, you have 16 nodes, 16 NUMA nodes on the 2-socket machine. So you will, if you want to place something in HBM, you would specify node numbers 8 to 15 because those are the HBM nodes. So any questions? Before we move on to Cache mode. Okay. Okay, so let's move on to cache mode then. Okay, so the cache mode, let's start with quad. Again, in the cache mode, HBM is transparent. Only DDR is visible to software. So which means that is when the CPU or when a core accesses memory, if there is an L3 or L3 miss, first it goes to the HBM cache. And if it misses in the HBM cache, then it will go to DDR, right? So that's how the hardware managed cache works. So one thing you have to make sure in the cache mode is your working set should fit in the HBM cache. This is true for like any cache. If you want to get the benefit out of cache, your working set has to fit in the HBM cache. If it doesn't, then you have to go to DDR and you will pay an additional penalty. And your latencies will increase because there are cache misses. So as I said, the HBM is not transparent, only DDR is HBM is transparent, and the only DDR is visible. So when you run your application, you could run as just another as you would run on a normal DDR machine because HBM is transparent. So to use these two nodes, you would use like MPI run with like 2 ranks, and each rank will fall on each socket, and you can easily run your application that way. Okay, let's go to the SNC. And here again, the same thing. This is cache mode with SNC4. Similar to quad, HBM is transparent, only DDR is visible. The only difference in the SNC4 mode is you have more nodes. So nodes 0 to 7 are DDR with cores, and HBM being transparent. Now, since there are 8 nodes, if you are running an MPI application, you have to run 8 ranks, and 8 ranks are multiple of 8 ranks. Then you can easily utilize the SNC4. I think this is the mode that the cluster is currently configured in. So you can use it quite easily. Okay, let's move on to the next slide here. So, but when you are using the cache mode, you have to be aware of one caveat, that is because HBM is managed as a cache, you can have conflicts in the HBM cache. That is, for example, in the picture on the left, you can see there is an HBM cache on a single socket is shown. So the HBM of 64 gigabytes of HBM is shown as a cache. And for the purpose of illustration, we assume here only physical address space of 128 gigabytes. So there are, in 128 gigabytes, there are two 64 gigabyte chunks. So what could happen is two addresses with the same offset as shown in the figure on the left they do map onto the same location in the HBM cache. So if both these addresses in the physical address space are accessed simultaneously, then only one of them can reside in the HBM cache. The other has to be replaced. So that's basically how a direct map cache works. And the HBM is managed as a direct map cache. And because of that, when there is a conflict, when two addresses map to the same address, only one can reside and the other has to be evicted. The unfortunate thing is the conflicts can happen with even small footprints. That's because of physical memory fragmentation. That is, even if your application memory footprint is less than 64 gigabytes. So you would think that, oh, since the memory footprint is less than 64 gigabytes, there shouldn't be any conflicts. But in practice, what could happen is the physical memory can wind up in any place in the physical address space. So because of that, that's called memory fragmentation. That's part of the Linux memory. Uh, that's a side effect of Linux memory allocation. The memory can be allocated anywhere in the address space. So even on a small application, uh, the physical memory pages can get fragmented, and two of those can map to the same location in the HBM cache, creating a conflict. So this is an unfortunate situation. To avoid that, as a workaround, we have a solution called fake NUMA. This is a Linux kernel solution. So when the machine is booted, in the kernel options, you can specify this fake NUMA options. For this particular example, you have to specify NUMA equals fake equals 2u. So the number 2 is equal. It means that divide the physical memory to two equal size nodes, fake nodes, fake NUMA nodes. So you will see more NUMA nodes when you use this option. So in this example, you will see twice as many NUMA nodes. But when you do this, the advantage is node 0 is filled before node 1 is used. So you are guaranteed that node 0 will be filled first. So if your application is 64 gigabyte of or less in memory footprint, it will reside nicely within node 0. So because of that, you won't get conflicts, right? Uh, the downside is that you will wind up with more fake NUMA nodes, but sorry, all of them share the same, all fake NUMA nodes share the same cores. So you don't have to usually take any additional steps to run your application as a user. You can use the same command lines which we showed you in the cache mode slides. Your normal MPI run commands, and it will run it will run fine, right? So as a user, you don't have to worry about or change the application command lines to use this fake NUMA, but this is something that the system administrators have to enable. And if you specifically went and looked at the number of NUMA nodes and so on, you will see a large number of NUMA nodes, but they are just a minor nuisance because you don't have to change the application command lines, and you can use it as the normal cache mode. Okay, so let's move on to the next slide. So there are a couple of resources you can use, especially for system administrators. You can refer to the configuration and tuning guide. There is a detailed guide, and for users there is a blog post with a summary of what's important to the users, basically containing this information that we presented here. So I think.
So yeah, I don't know, any questions so far?
Yeah, I guess for me, I mean, sorry, I'm obviously I think probably not sort of into the detailed hardware enough to kind of understand all of this. So just as a kind of summary of this, so essentially the high memory is used, in preference to kind of the caching hierarchy you would normally have on memory. Like my understanding is, you have the sort of L1, L2, L3 cache, and the idea is that this high bandwidth memory would be used first, right? So that's the thing, and it's significantly faster than any of um the traditional kind of access to RAM. So I know this is a very, very basic question, but I want to kind of understand what the use case would be. So would it be where you're loading vast arrays of, say, molecular data in our case, doing a calculation and saving that back? Those kind of applications would be vastly accelerated in that case. Is that right?
Yeah. So HBM, as you said, it's a memory side cache. So it's you can think of as the last level cache. right? When HBM is present. So first you have L1, L2, L3, and when there is an L3 miss, then it will go to the HBM cache,
So
right?
it's after the various kind of smaller levels of cache, and it's 64
Exactly.
gig of. So for anything of the size of 64 gigabytes and less, you should be seeing fast speed ups if your entire problem can fit within that 64 gigabytes.
Exactly. So it is as using the HBM only mode. If your working set can fit within the HBM size capacity, then you should see speed ups.
Okay, so then when you go beyond that, so let's say your job, your problem size goes beyond 64 gigabytes, then it's going to have to go essentially to the next level of DDR, essentially like another level of cache. That's the way it acts, if I understand correctly.
Yeah, so you will go to the normal memory if your working set size is larger than 64 gigabytes. Uh, your actual memory footprint can be larger, but as long as your working set is within 64 gigabytes, you will get speed ups. You will hit in the cache uh, the amount of data that you are using at a single time, right?
Okay, so in terms of a kind of a rules of thumb that we should be thinking for our user community, kind of job sizes that we should be targeting would be something where, a particular, I don't know, inner loop of a calculation can fit within that 64 gigabyte, something like that. You'd
Yeah.
expect to see significant speed up. Is that right?
Yes. Exactly.
Yeah, interesting. So I mean, this has implications for kind of job sizing. So when people are choosing what kind of cases they would target with these nodes, and I guess for development, so if people are developing their code, they would maybe think about chunking up problems into these kind of blocks. Is that something that would be worth considering, or?
Yeah. So yes, especially if the memory footprint is larger than 64 gigabytes, you should think of L4 as another cache, and you should cache block to it uh, to get the most benefit out of it. Yeah. So you would manage as any other cache.
Yeah, I mean, as someone who writes quite a lot of
Yeah.
code, but I'm not a software engineer. I very rarely think of the caching or memory. So I mean, this talk I would say is
So,
probably a slightly lower level than I'm used to thinking. I'm not sure about the other people here whether they have a
so
set.
I mean, the other thing is that like when you write the code, I don't know how like if you run on multiple, here's multiple MPI ranks and you scale to multiple nodes, right? I mean, even don't think about when you have this type of technology on the normal CPUs, like when you scale to multiple nodes, then your memory footprint also sometimes comes down, right?
Yeah,
So that's the other way that you can still run and fit in 64 gig of. So if you have a memory bandwidth sparing application, um, so I mean, don't maybe uh, s- when you more and the capacities, the memory capacity is much higher than 128 gig per node or 64 gig per socket, then if it is an MPI application that you kind of scale up and then memory footprint comes down, automatically that applies here as well, right? So when you scale on 3 nodes, you can still fit in the HBM and benefit from it without needing to change code.
can we go back to the slide before where you talked about the processes and their link to the different HBMs, because that's I think a really important point. Here, no, but this one here, yeah. So the different
This one.
no, I think two on from that. So 13, 14, maybe 14. Um, is it 14? Yeah, maybe. Yes. So yeah, this one here. So each node has so just physically the high bandwidth memory, the 64 gigabytes corresponds per node, right? So let's say you had, I think we've got, I mean, I'm not sure if the high bandwidth memories are 40
Yeah.
per node, but typically
So each of these are 16, yeah, 16 gig.
so you've
So
got
there,
so you've got for say 40 core node, you have 64 gigabytes assigned to that. So again, that would be something maybe that we would consider in the job scheduler, or in terms of the actual run script, or would that be something you would, as a user, have to think about in terms of making sure when you do your calculation of division of processors to amount of memory, you would be trying to balance this, like you say, to make sure you're not going beyond the HBM.
Sorry, sorry, can you rephrase, ask the question again?
So just to be clear, right, we've got, say, a node which has a linked set of high bandwidth memory. So that would be 64 gigabytes linked to, say, a 40 core node. Is that correct?
No,
So-
no, it's not that. So
Yeah.
it's per socket, and these are the nodes have 2 sockets. A number of cores is not 40 for these ones. So it's 64 cores in total for one of these nodes.
64 cores per node, and we have 64
So
gigabyte.
maybe let me so this is one CPU that you can see in the top, okay?
Yeah.
This one CPU has a multi-tile architecture. So the 4 thing that you saw in a slide 16, it's the cores. All of them will belong to one socket, one CPU. It's just organized into 4 different tiles. So if you have a 32 core, you have a 32 core CPU here. Each of these tiles, it has 8 cores per each of these tiles, and each of those is connected directly to a 16 gig HBM. So I mean, these are all abstracted in the software level from user perspective or software perspective, and when you put it in SNC4, kind of automatically handles, improves latency, making sure your memory access goes to the right memory channel and so on.
I get that, but also being aware that it's, I guess, an 8 core to 16 gigabyte HBM is very, very probably the important thing for our user community to understand, because that's the thing that determines how they basically allocate resources. Is that fair to say?
I think so, right, Rashira?
Sorry, I appreciate it. I mean, asking me stupid questions.
No, it's no a stupid question. I think it's good that you ask. So you think what is needed from your users.
Right. Yeah. So if you make sure that your memory footprint is less than 16 gigabyte for NUMA node, right? In SNC4, then they don't have to make any special thing at all, because it will fit within HBM. HBM capacity, then they don't have to modify source or something. And as Fouzhan said, you can achieve that by scaling to more nodes. For example, if you have a strong scaling application, as you move to more nodes, your memory footprint on a single node will be smaller. And so you can use that technique to reduce the amount of memory footprint per node. And as long as the memory footprint is less than 128 gigabyte total for 2 sockets, then it will fit within HBM.
And when you say socket, a socket is is one of the 64 gigabyte HBMs, right?
Yeah.
Okay, fine.
Yeah, 2 sockets. There are 2 sockets per node, like S0 and S1 in this picture are 2 sockets.
So 2 sockets per node, 64 cores per node, 8 cores per NUMA, and 16 gigabytes linked.
Yeah. So I don't know the exact specification of the core count of the CPU that you have. These are different core counts. So
That's
so
fine.
someone
What I think we'll do is for our website, we'll summarize this information and just kind of some nice rules of thumb. I think that's probably the most useful way to help people. So we've got kind of roughly what you should be targeting for those sizes, I think, based on this. Just to make sure people are kind of in that sweet spot of making sure they don't go beyond the HBM.
I would like to ask a question, Ed, if it
Please,
is
yeah, sure.
So basically in our applications, what we have is we are building very big matrices, right? So in DFT, we are just calculating, like usually the workflow is the following: you have a very big matrix, Then afterwards you diagonalize, and then you basically apply any methodology for kind of an obtaining not only eigenvalues, eigenvectors, but you are doing this sequentially for obtaining like forces and things like that. Yep. So my question here is, you are forced to kind of like fine tune the sector, so the 64 gigabytes, to fit that matrix to get the best performance. Is that correct? So that you have to play with the MPA ranks, so seeing more or less if this amount of ranks are basically filling this 64 gigabytes, otherwise you will be hitting, or you will be actually like not getting the performance that these kind of nodes could provide. Am I correct, or I'm missing something here?
Okay, so there are two things. Depending on the mode. So if let's look at, so currently the flat mode is shown. So in the flat mode, if your application is not memory bandwidth bound, you can use the DDR capacity entirely. You just run your application and you use DDR on this machine, and you can use any amount of memory. There is no 64 gigabyte restriction because you are using DDR. You can use the entire DDR capacity in the flat mode, right? So if your application is not memory bandwidth bound. Now, if it is memory bandwidth bound, and if you can benefit from memory bandwidth, then yes, you are right. You have to place your application, you have to size your application so it will fit within the HBM. Now that's for the flat mode. In the cache mode, it is, you can, if you want to guarantee that it fits within HBM cache size, then yes, you are right that you have to, you got to look at the MPI memory footprint and make sure that it is like 64 gigabytes. But usually what matters is the working set size, not the memory footprint in the cache mode, right? So your memory footprint can be a little bit larger, maybe 2 times larger. But as long as you operate on 64 gigabytes of data at a given time, you can exceed the HBM capacity in the cache mode. Is that clear?
Yes, I understand. It's just, I mean, it is a little bit complicated for us to kind of set up the memory beforehand. And this is actually something that is very complicated for many of these applications because you are not very sure. It depends on many variables that you are using in the end. Yep. So you can kind of model one of these systems depending on how big you want some variables or not. And then the matrix size could vary like widely. So the range can be very, very up, and it just depends on a couple of variables that you would like to. So the issue that you might, yeah, so we might need to make a benchmark more or less to get an idea of what is the memory footprint. That is my impression, at least for this, because it's not very clear to me that we beforehand, before launching any calculation, you could in principle get the correct amount of memory that you are going to use beforehand. Yep.
Okay.
So
okay,
this is
yeah.
for the main kind of purposes of software that we use for making calculations. It is very complicated to set up. I mean, I understand if you are developing your own kind of a program and so on, then the same Fortran, whatever, you just basically put memory allocatable, then you set something, a fixed variable, and that's it. You are sure that you will do this. Because the other option that we have been using is this, what is this, OMP, the export OMP stack memory. I think that is the option that you have for like setting a very kind of a hard, yes, I think that is a stack size. That is the one that is actually kind of used in many codes for setting a hard code amount of memory that you would like to use. Yep. But the issue is that beforehand, for many of the programs of software that we use, you cannot really define the amount of memory that you would like to use. Yeah, or you are, yeah, you use. That is the main problem that we have. Like for instance, Ed was saying like VASP or I don't know, CPTK or things like that. You don't have that control on top of that part of the software. that is a problem.
Okay, I understand. Yeah,
So
yeah.
I mean,
So
we sometimes we use this kind of trick that you have this OMP stack size, and then you can define the amount of memory beforehand, like play a little bit to see if this fits into the memory of the node or not, to increase it a little bit more or not. But so far, what I see is that we might need to make a benchmark for this kind of software already developed and that we are using.
But I guess the point was also made that you can somewhat control that with your choice of MPI ranks, right? You can just parallelize across nodes.
True, but the things that so beforehand you don't know. That's
Sure.
You have to benchmark. All right, thank you. So that was my question. Thank you very much. That clarifies.
yeah, so if you are using the flood mode, there is another option. It's not. If you use the membind option, the application will not allocate more than HBM size, but your concern is still valid. So, but at least you know that it won't exceed the HBM capacity if you use -M option, or with the NUMA control, or with the Intel MPI if you use HBM bind option. If you use bind options, then you are guaranteed that it will not exceed the HBM capacity. So the worst thing that happens is the application when it exceeds the memory capacity, it will fail. But you know at least that it is guaranteed that it is using the HBM and not spilling to DDR.
That's a good advice. Yeah, absolutely. We might need to use that kind of as a starting point. Yeah, thank you.
Yeah, I guess this is the cache mode. The easy use is the other way around, right? If you don't do any of those, it's like it would run, but if it goes over, then you lose performance benefits. So it kind of depends on maybe what experience you kind of find out. So that's yeah, it's knowing it of course helps to choose the best performance. In terms of applications, like we have done lots of benchmarking ourselves, so and also, I mean, this was launched 2 years ago, right? So there are a lot of benchmarks also probably available publicly from other centers and so on. But just again, I mean, you know the code, whether your code is bandwidth bound or so. But like, for example, sort of GrowMax usually is not something that benefits from bandwidth, improving memory bandwidth, right? It's usually cache bound. But things like OpenFOAM, for example, most of the test cases use quite a speed up. VASP also is something that, I mean, I think OpenFOAM was one that we more or less on most of the anything we tested, we saw a huge performance with HBM. VASP, that also we did see. So this is let me see. So this is some like overall a few. Again, you don't have Earth system modeling that much in your user community. This is if you have AI, some AI workload. But so VASP you can see here. So here is reference comparing with Ice, like the gray one is Xeon scalable, or Xeon 4th gen without HBM, and the blue one is with HBM. So you can see, for example, if you look at GrowMax, you don't see performance improvement with that. VASP, I mean, again, these are geomean of a set of workloads, but you kind of have to test. So things like quantum espresso depends on the workload, VASP as well. Where your memory bandwidth bound and you can fit, you can see the benefit basically. So these are compared using I think these benchmarks are done on 56 core SKU and also on a HBM only mode. So right, they all fit the 64 gig, sorry, in 128 gig pen mode. But yeah, we did, I think, some benchmarking with cache mode and so on. So as long as it scales and fits in the memory, you can kind of see the benefits there.
I just
So
ask, so on the deep MD training is potentially interesting to the community. Any idea why that's so much better on that one, 2.9?
this,
Yeah, so that looks again something that potentially is a use case for people.
okay. I don't know the application. Do you know, Rashira, by any chance? Is it, does it have some,
So I think it's
is it this? No, it's not DeepCam. I
So,
think it is
so
this
this would
one.
fit within this
Yeah.
community in that you're training
Mhm.
potentials that would come from, say, VASP, as far as I understand it, to be used as kind of classical systems. So that deep MD would be a potential use case for people with
Okay.
materials modeling. So it's interesting to note whether or not that would also then apply to other machine learning style potentials, because as far as I understand, DeepMD is one type of potential, and there's obviously other ones. The only thing with that is that most people, I guess, would be targeting probably GPUs or CUDA with that type of training anyway.
So this is, yeah, so I mean, what you see here comparing with, because it's basically comparing the same CPU architecture, the difference here is just DDR versus HBM. So the performance improvement comes here. It's due to HBM, right? But overall, if you have some AI training, depending on the data types, because from the Sapphire or a fourth generation, basically we have AMX units. So like the same way like that, each core comes with a AVX 512, right? We have this units with each core AMX advanced matrix multiplication that has a 2D tile and units for matrix multiplication. So that speed up some of the AI workloads as well. Like, of course, it's not something that when you need a high-end GPU to do a high-end training, that's not the case. But when you have kind of AI within your workload and you're doing inference, that's also a speed up the workload, and most of it also like upstreaming and PyTorch and so on. So people again don't need to change anything to benefit from it. So it's good for your community to be aware of it, let's say. I don't know if that answers the question.
Yeah, I mean, I think certainly people are using would potentially using that particular package, or at least anything which you're training a model potentially could consider that. Because the big problem you have with GPUs, in my understanding, is you're generally struggling maybe with memory and the amount of memory available, and so these cards, although it might be slightly slower than say using a pure GPU solution, might provide an attractive possibility for training. So again, it'd be interesting to see from the community who's using those tools and if they would be able to benefit.
Yeah, I think it's if they are aware of it and they kind of start using it, I think you build a lot of knowledge on it as well, right? It's about being aware that it exists, and like if also it depends what you measure. Like when you have to run on GPU, you have to move to GPU, they move your data, all of that. But if you consider all your workflow, it sorry. Sorry, I got one of my other
Oh no,
cause of coffee. Yeah, so it's good for them to know it is there, and then if you need any more information or other training from us, we can kind of come and do that as well. If you see that developing.
Yeah, I mean, I think there's definitely an interest, increasing interest in these machine learning potentials, and
Yeah.
realistically, a lot of the use case I think is running when we're running kind of generally kind of quantum chemistry, but obviously the future of that appears to be training models. It's interesting you're outperforming an A100 there with that. Is that the fourth generation? Is that the
So so the first generation is is yeah, fourth generation is sweet. So I mean, the features has improved a lot for the latest one. So the fourth generation had up to 50, so up to 60 core, sorry. So this is a 56 core version. The latest generation, Xeon 6 has up to Xeon 6 P-core have up to 128 cores. So it's a huge performance speed up comparing with the fifth gen. So it's more than like usually across the board. I mean, more than 2x, like because you basically put 2 times number of cores, right? We had up to 64 on fifth gen. So with Xeon 6, we have up to 128 cores. So if you at the top SKU, you have double number of cores. The memory bandwidth also massively increased, which is also again important for most of AI workload, because we have, so this was 8 channel that becomes 12 channel, and also we have like support of MRD, which are also again helpful for memory bandwidth application, bound application, or memory bound application overall. And then let me see, actually I might have some slide there. So there is a huge performance improvement there, sorry. And let me see if I have any AI one. I didn't expect we go to the Xeon 6, but yeah, there is also lots of public information, to be honest, on the performance for the CPU there. Yeah, so when it comes, especially if like I wouldn't say for high-end training in any way, but like if you have also more AI work, I mean, if you need to do inference during part of your simulation and so on, it becomes, I think, quite an interesting solution, to be honest, and it's cheaper, right?
Because inference, I guess, if people are starting recently to use these machine learning trained materials model,
Yeah.
that essentially is an inference problem.
Yeah.
And they're not massive. They're generally
Yeah, exactly.
small compared to some of the language models.
So
But certainly, if these are performant for those,
yeah.
they're available, then that's another possible use case. Which
Yeah, I think I think that's something that, but yeah, people need to be aware, right? So, and I was talking to somebody a while ago, a scientist, I think was one of the UK university. So he was saying like, yeah, I can run on CPU and I don't mind waiting a bit, maybe even longer, but as long as I get my job done. I mean, for the scientists, doesn't matter what they run, right? They need the results. So,
that's not like when you
availability.
have CPU codes,
Yeah.
or anything. Just out of interest, how has this been benchmarked for, say, something like DeepSeek or one of the large language models? Would they run on instead of these nodes?
I mean, it depends on the size and so on. But yeah, I mean, we have, let me just stop this. Maybe I have some,
That's about 700 gigabytes, I guess, for a big model. It's no, it's a use case that again I can see some
yeah.
potential applications for people looking to say run kind of smart simulations where it's generating input files on the fly. I think this is a little bit further down the line maybe, and
Yeah.
maybe not so relevant.
So we have, I can look and send you some of the things because so I mean some of the benchmarks that we already done more on what is already done on the AI side. Some of it, as I said, could be already publicly talked about when we launched the product. Sorry, I don't have it now handy to share it, but I can send you those. Whether DeepSeek in itself has been benchmarked or not yet, but I need to check because sometimes also it
But
takes a
we
while
would
to
expect
check.
to.
Yeah.
But you
Yeah.
mentioned a use case like that would potentially benefit from high bandwidth because that's.
I mean, inference, yeah. So, yeah, it would benefit. So if you look at, let's see if I have the product actually quickly. Um,
I guess in the interest of time, Faisal, was any other questions from anyone on the hardware while from where I've been looking?
Sorry, I forgot we are out of time.
No, we didn't. We have an hour and a half for this.
Oh, okay.
So yeah, there's plenty of time. But I mean,
So it is the Xeon 6, and as you can see, it's even lower core counts that get messed. So the results I was showing on the other one was comparing with 4th gen. This is comparing 6th gen with 5th gen. So you can get more of that. So I think these are the standard one on AI that have been done. This is again comparing.
something like Linpack might be relevant.
I mean, Limpack, yeah. I mean, Limpack is straightforward, like you see. This is for comparing. Yeah. So Xeon 6 and the first column are basically performance, second column are performance per watt. So the impact has got about more than 2x. When you have something that is more memory bound, like HPC, you get more than that with MOD.
Because I guess this comes back to Alejandro's question about
Yeah.
forming a big matrix, and so
Yeah.
something like Linpack is going to be one of the backends that would do that.
I mean, if sorry, if there's compute bound, then but yeah, so you can fit more memory, and then when it goes to AI, then these are like examples. I mean, so yeah, Llama 2 and 3. I mean, Llama 4. So it's progressing quickly, right? So we try to also benchmark it as soon as things happen. So this data is about 6 months old because it was used when we launched the product, but it should give you an idea of performance improvements.
Right, brilliant.